Okay, so now let's get started with the first function that is moving in a straight line. I'm going to show you how you can do this in both Python and C++. So let's get started with the Python code. And here we have the Turtle Sim Simulator. And let's assume that the turtle is going to start from an initial location that is x0 and y0 and has to move in a straight line until it goes to the location x and y. So what we should do here, we should actually keep track about the position of the robot every time and try to compute at every time step how much distance the robot has moved. Okay, so let's look at our move method here. First, the move method, it contains a velocity publisher because we will be using a velocity publisher to publish any new twist message. And we have to specify the speed as argument. What is the speed that the robot has to move with, and also the distance to move. And here we specify the direction. Is forward can be equal to true or false. So if the direction now is forward is equal to true, then the linear.x speed must be positive. So here we use the absolute value of the speed to enforce and to ensure that the linear.x has a positive value, and this will make the robot move straight forward. And in the case of is forward is false, in this case we are going to set the value as minus the absolute value of the speed, and this will ensure that the robot is going to move backward direction. So forward direction, the speed has to be positive, and backward direction, the speed has to be negative. And then the first thing we need to do in the move method, we need to create a velocity message of type twist. So initially all the values x, y, z for the linear component and the angular component will be equal to 0, and we will keep them 0 only, but except the x component. The x component has to be equal to the speed value provided here as an argument to the method. So now the robot is ready to move. Initially, the distance moved is equal to 0, and then we are going to make a while loop, okay, and start publishing the velocity message. So the robot here is going to start its motion. So when it starts its motion, its velocity, its coordinate x and y is going to change. So the distance moved is going to change. So every time I'm going to measure the distance moved using the Euclidean distance equation like this, which is the square root of x2 minus x1 squared plus y2 minus y1 squared. So I implement this here in Python. I will calculate the distance moved, and if the distance is greater than the desired distance, if the move distance is greater than the desired distance, then in this case I will break the loop. So when I break the loop, I will make the robot stop immediately by setting the linear.x value to 0. So remember here we have set it to some specific speed value which can be positive or negative, whether we want the robot to move forward or backward. But when we reach the desired distance to move, we are going to go outside of the while loop and then force the robot to stop by just publishing a message with linear.x equal to 0. So of course here we need to have an up-to-date value of the current position of the robot, and for this we are going to use the global variable x and y, which are defined globally, and they are updated into the callback function, into the pose callback function. So if you look at the code, we have defined a pose callback function that will take the global variable x, y, and u, and every time that there is a new pose message that is received by the subscriber, because here we define a subscriber, turtle1/pose, okay, pose subscriber, and whenever there is a new message, the pose callback method is going to be executed. So what happens when we execute the pose callback method? It will take the new pose message that comes, that contains the up-to-date value, and then we'll put the value of x equal to pose message.x, y, that is the global value y, pose message.y, and the u value, that is the orientation of the robot, equal to pose message.theta. So I will be sure that the x, y, and u value will always be up to date, because this subscriber is going to update these values whenever there is a new pose message that comes. So here we can actually calculate the distance moved using the Euclidean distance, which will be equal to x, that is the up-to-date position of the robot minus x0, that is the initial position of the robot here on the map, okay, square plus y, that is the current location of the robot, minus y0, that is the initial y coordinate location of the robot, square. So this is going to be exactly the same as in the equation. So once we calculate the distance moved, we are going to check if we have exceeded, if not distance moved smaller than distance, or we can say just if distance moved is greater than the distance, just to break the loop and force the robot to stop. Okay, so the same thing will be done in C++. Of course, here just we have the language difference, but here I have used a different technique to calculate the distance moved, not using the x and y coordinates, but I have used the equation speed multiplied by time is equal to the distance. So basically the header is the same. We define the speed, we define the distance, we define the is forward, whether it is in the forward direction or backward direction. We do the same thing as in Python, but in the C++ language. But in order to measure the distance, the difference here is that the way I have measured the distance, just using the speed, which is provided as input, multiplied by t1 minus t0. So t0, I'm going to take the instance before starting the motion, which will be the current time before starting the motion, and then we will do a while loop. So while the current distance is smaller than the desired distance, we are going to calculate, we are going to publish. So when we publish, the robot is going to move, and here we will estimate the current distance. So the estimation will be the speed multiplied the elapsed time, and I'm going to take every time t1 and make the difference with time t0 to find the distance moved. And then I will compare the current distance with the desired distance. Once the current distance is greater than the desired distance, like we did in Python, we are going to exit the while loop, and we will force the robot to stop by just publishing a velocity message with the linear.x equal to 0. Okay, so these are two techniques to make the robot move straight. You can use the equation speed multiplied by the time difference, and also you can use the technique here. You calculate the square root of the distance moved by, and in this case, of course, you need to subscribe to the pose of the robot to have the up-to-date value of the robot position to be able to calculate the distance moved at every time. But I want to add a note here that the way that we have calculated the distance moved is not the best way to do it in ROS. So basically, the best way is to use transformation. This is a very advanced concept. We are not going to cover this even in this first course, ROS for Beginners 1. But it is covered in the second part of the course with navigation and SLAM, because this is related to the navigation. Because we need first to understand what are transformations, how they are implemented in ROS, and how to use them later on to calculate, for example, the orientation or the distance moved of the robot. This is going to be discussed in detail in the second course about ROS for Beginners 2, navigation and SLAM. And in both cases, of course, we need to make ROS.py.rate. Here we are going to publish 10 messages per second. And I'm going to show you now in a demonstration what is the impact of the ROS.py.rate, okay, with respect also to the speed. Let's now make a small demonstration about the move straight. Okay, now let's make a demonstration about the move straight method. So here we have the main function. Of course, in the main function, we are going to initialize the turtle sim node motion, and we are going to create a velocity publisher that we will use to publish twist messages on the cmdvel topic, which is turtle1/cmdvel. And this is the subscriber that will subscribe to the position topic, the pose message. And of course, here we are going to need the pose message to get the up-to-date values of the x and y coordinates that are already explained in the slides. And this is the method now. We are going to call the method move velocity publisher, and it will move at 1 meter per second for 4 meters, and it will move in the forward direction. Let's look at the method move. It's available here. Okay, it's the same method that I have presented in the slides. And here we are going to use the Euclidean distance in order to measure the distance moved. And once the distance moved is greater than the desired distance, we are going to exit the while loop and then force the robot to stop by setting the linear.x message equal to 0. Okay, so let's try this method now. We are going to use the command rosrun, ros essential cpp turtle sim underscore cleaner.py. It will run our code, and you will see now the robot is moving for 4 meters, okay, at a speed 1 meter per second. So you can see it has been, it spans 4 seconds in order to move the 4 meters. We can do the same if we want to move in the backward direction by setting these to false. That's pretty much easy. And then running again, it will make the robot moving backward, and it will stop exactly at the same location from where it has started. Okay, so this is now the robot moving. Let's now look in more details about the effect of the rate here. So here we are publishing at the rate of 1 message, 10 messages per second. So it means that every 10th a second we are updating the position of the robot, and you are measuring the distance moved, and you are taking the right decision whether to keep moving or to stop. So now let's see what happens if we change the value to 1. So in this case, we are going to update the position of the robot once every second and not once every 10th a second. Of course, this is going to provide less update for the position, and this may lead the robot maybe to move a little bit further than the desired location. So let's do that. I'm going to put this to true in order to make it move forward, and we run again the executable turtlesim cleaner.py, and the robot is moving as you are seeing. So in this particular case, it stops almost in the same location, so we didn't see any much impact of the loop rate, changing it from 10 or even to 1. Why? Because here the velocity is very small. Okay, imagine that I change the velocity now. For example, I will put it 6 meters per second. Okay, and let me put the robot moving back. So you can see now this is the start location, and I have changed both the velocity. I make it much higher. Instead of 1 meter per second, it will be 6 meters per second. And here the loop rate will be just equal to 1. So let's see what happens when we do this. I'm going to run again turtlesim cleaner.py, and then the robot is going to move, and you can see it has exceeded the origin location. So why there is an extra motion here? Because we update the value of the pose x and y once every second. And since the robot is moving at very high speed, so during that second, okay, it has moved more than it should, because we didn't update in the right way or in a sufficient way the pose of the robot to calculate the distance. So if I make true again, okay, of course it will have the same behavior but in the forward direction. But now if you are moving at high speed and you would like really to control the robot to be at the exact location, in this case you have to play with the rate. Okay, so the rate here shouldn't be equal to 1. If I put the rate equal to 10, for example, we will see that the robot is going to move exactly or almost exactly 4 meters. Okay, it will move almost exactly 4 meters. Let me make this to false. And running again the executable, you can see now it's moving back, and it didn't move for the extra distance because now we have much higher loop rate, so we are updating the distance moved much more often. Okay, we can even make it higher if we want. Let me move forward. So if you put the loop rate very high, in this case the control will be much smoother. But of course, the drawback is that you are going to consume much more bandwidth. Look here, it's only 4.12 the distance that was the distance traveled, a little bit more than 4.0. Okay, if you use, for example, even higher one, let's see, for example, 100 loop rate, and let's see here the distance moved at this speed still. I will make false here. Okay, and it's moving back. It's 4.03. So just the error is only 0.03 because now the loop rate is much higher. Of course, so you need to make the loop rate based on what is the value of the speed here. Okay, but you can reduce the speed. In this case, you can also reduce the loop rate, and you should not have any issue. So if I run now at the speed of only 1 meter per second here, and let me make it in the true direction, forward direction, and here I have a loop rate of 10 messages per second. That should be fine to have a decent value of the error. Okay, so here the robot is going to move, and it will be 4.09, so only 0.09 as an error. Okay, this is just to explain you the effect of the loop rate on the control of the robot. Okay, so now we have already completed the move straight. In C++, it's the same. So this is the code in C++. I have already presented it in the slides. So first of all, we declare the headers of the method. This is the way that we do it in C++. And this is also our main function. We define a publisher and a subscriber, a publisher of the velocity of the twist message on the same topic, turtle1cmdval, and here the pose of the subscriber, turtle1/pose. And the other thing is pretty much the same, so you can call the method move and make the robot moving. So we define all the different methods in the same way. You can test this method if you want. Here we are using a different technique for measuring the distance based on the speed multiplied by the time duration. Okay, so now everything is fine for the move straight method, and now let's talk about how to rotate the robot in place. Okay, so let's now talk about the rotate function. I'm going to show you how to make it in C++ and Python. And let's start by the Python code. So here we have a robot, and we want the robot to rotate in place with a certain angle. And it has to be noted that in ROS, we use the radians as the unit of the angles. But we as human beings, we maybe don't understand very much the radians notation, and we understand much better the degrees, the notation of angles in degrees. So here, if you can see in the header of the rotate message, we are going to provide the angular velocity in degree and the relative angle to rotate in degree as well. And we are going to convert it later on to radian inside the code, because this is much easier for you to input the values in degree rather than in radian. For example, if you want to rotate 90 degrees, you can just write 90 instead of just converting this value manually to radians. And in the same way, we define a velocity publisher, because we are going to publish a velocity message, a twist message, and we define whether we want to rotate in the clockwise direction or in the counterclockwise direction. So in ROS, the rotation in clockwise direction, it means that the angular velocity is negative. And the rotation in the counterclockwise direction, it means that the angular velocity is positive. So the first thing here, depending on the flag, whether it is true or false, we are going to set the value of angular.z to either negative value or positive value. So in case of clockwise, we set the value of angular velocity in the z component to a negative value, which is minus the absolute value of the angular speed provided. Okay, angular speed provided, and else it will be the positive value of the angular speed provided. So look, that angular speed variable here is just the radian version of the angular speed degree provided by the user. For example, if you provide the value 20 degrees per second, first we are going to convert this into radians per second, and then we will use them as for the value of the angular.z velocity here. Okay, so this is about the clockwise. And then in the same way that we did with the distance, we are going to define a loop rate. And now we understand what is the effect of the loop rate. I think 10 would be a good value if we don't rotate at a very high speed. And we will use the time difference, so the velocity multiplied by the time, in order to find the rotated angle. So in move straight line, we have calculated the move distance over time, and now we are going to calculate the rotated angle over time. And this will be simply the angular velocity multiplied by the time. So we take t0, it's the instance before starting the motion, and inside the while loop, we are going to publish the velocity message, so the robot starts to rotate, and we are going to measure every time the t1 value, so the current instance. Then we do the duration, that is t1 minus t0, and based on this, using the information about the angular velocity, we can estimate the current angle rotated in degrees. So if the current angle rotated is greater than the desired angle, that is the relative angle to rotate, in this case we are going to break the while loop, and then here we are going to impose the robot to stop by setting the angular velocity z component to 0, and then we publish the message to make the robot stop. Okay, so basically it's the same structure as the move straight. The only thing here that instead of measuring the distance moved, we are going to measure the rotated angle, and we will compare the rotated angle to the desired angle to rotate. That's the whole thing. Otherwise, it's pretty much similar to the straight moving straight method. So likewise in C++, we can define the same method. Okay, so here we specify angular speed in degree and relative speed in degree. In the C++ version here, the angular speed and the relative speed are provided in radian, so we don't do any conversion over here. And this is a difference, but of course you can define this in degree if you want, and then make the conversion like I did in Python. And here we define clockwise and counterclockwise in the same way that we did in Python. We are going to set the angular z velocity values to either negative or positive, depending whether it is clockwise or counterclockwise. And then we calculate t0, we calculate the current angle, that is the angular speed multiplied by the time. And here, when you publish a message in C++ API, you need to call ROS spin once. Okay, so if you see here in Python, we don't have ROS spin once. We don't use it. We use only ROS spin for subscribers. But for C++, when you publish, in order to dispatch the message, you need to use ROS spin once. Okay, it's been only to dispatch one message, and then you are going to sleep for some time based on the loop rate here. So here the sleeping time is going 1/10 of a second. And we will keep doing this in the while loop until the current angle becomes greater than the desired angle to rotate. And if this is the case, we are going to set the angular velocity to 0 and finally publish the 0 message in order to force the robot to stop. So now let's see a demo again on how we can do this with ROS. Okay, so now we are going to test the method rotate. This is the method. This is the C++ code. Let me go to the Python code. This is the method rotate here. We specify a velocity publisher, the angular speed in degree, the relative angle in degree, and the orientation, whether clockwise and counterclockwise. This is the same code that I have presented. Of course, we don't need to have the velocity publisher inside the method because it's already defined outside. And now let's try to run it here. So I'm going to go to the main function. I will deactivate the move method and the rotate method. So it's really a good practice that you try your method one by one before integrating them into the whole solution. So you have observed that we have first tried the method move. We made sure that it works. It responds correctly to the different input that we provide, and it provides the expected output. So we'll do the same for the rotate method. And here we will provide the velocity publisher, and we would like that the robot will rotate at a speed, for example here, 30 degrees per second, and a total orientation of 90 degrees. And we want that it rotates in the clockwise direction. So let's try to execute this. You can do rosrun essential cvp turtlesim cleaner.py, and running this, it will make the robot move as you already mentioned. So you can see now this is moving in the clockwise direction, and it has rotated 90 degrees. Okay, so if I do the same again, it will rotate 90 degrees more. Okay, so it's working fine as expected. We can rotate into the counterclockwise, so here we will provide a positive velocity. Okay, so let me rotate this. Okay, now it's rotating in the counterclockwise. So if you want to see the velocity, we can use Rostopic list. So let me put this at very low value. Okay, so that it rotates very slowly. And here we are going to try to make Rostopic echo and turtle 1 CMD value. Okay, I'm going to rotate this again, and we will see here. So you can see now the value, it's positive. Okay, you can see the value, it's positive because it's rotating in the counterclockwise. Okay, now if we change this to clockwise, so let me put this, for example, through here, to rotate in clockwise 90 degrees. We do the same thing, and you can see now that the angular velocity becomes negative because it is rotating in the clockwise direction. So in the same way that we did with the move straight, the loop rate here is very important. Okay, so if I make, for example, very small loop rate, and I can make here, try to make very high angular speed. So let's see what happens. Okay, you can see now that the robot is going to rotate even more. Instead of 90 degrees, it rotated even more. Okay, because here the loop rate was very small. Okay, so if you want to rotate at high speed, you must make sure that you put a loop rate that is high enough. Let me try, for example, 20. And now I will ask the robot to rotate 90 degrees. And you can see it did it right because I have increased the loop rate. Okay, so this is an illustration of the rotate function. And now let's move to the next behavior, that is the go-to-goal behavior. In the previous lectures, we have talked about the move straight method and also the rotate method. So for the move straight, we need to provide the speed, and we provide also the distance to move, and the robot is going to execute that accordingly. And for the rotate method, we need to provide the rotation angle and also the angular speed, and then the robot is going to act accordingly. Now, for the go-to-goal method or go-to-goal behavior, things are a little bit different, because in this case we are not going to provide neither the speed nor the angle to rotate, but we are going to provide just the destination or the goal location. And the robot has to adjust accordingly and dynamically its speed and its rotation angle, so the linear speed and the angular speed, in order to go to the goal location. So I'm going to show you how to implement the go-to-goal behavior in both C++ and Python, and I'm going to introduce also some concepts about the feedback control. So this is now the Turtle Sim simulator, and let's assume that we have a robot that is located initially at the location x0 equal to 5 and y0 equal to 5, and the orientation data equal to 0. And then we would like to the robot to move to this goal location, which is equal to x goal equal to 1, y goal equal to 1, and theta goal equal to a certain value here. So in this case, the input to the function will be, of course, the velocity publisher, because we are going still to publish velocity and twist messages, but we just need to provide the goal location and their x and y coordinates. So I have here x goal and y goal. And then we are going to implement a controller to make the robot move into that direction. So the controller, we are going to control the linear velocity, and we are going to control the angular velocity so that the robot moves smoothly from the original location to the goal location. So let's see how we can do this. As we did before, we are going to define a twist message that is called velocity message here. We are going also to consider x and y and u as global variables, because remember that these variables are updated into the callback function, the pose callback function, so that we have the up-to-date value of the x coordinate, the y coordinate, and also the orientation of the robot. And then inside the while loop, we are going to implement to calculate the distance between the current location of the robot and the goal location. Of course, for the calculation of the distance, we are going to do the same thing. We're going to use the Euclidean distance to calculate the location in the same way that we did in the move straight. And then the linear speed will be a function, will be proportional to the distance. So you can think about the distance as the error, okay? As the error that we try to minimize. So we need to minimize the distance between the current location and the goal location. And for this, what we are going to do, we are going to implement a proportional controller, okay, such that the linear speed will be just proportional to the distance. So here we define a constant k linear. So for example, we can put a value of 0.5, and then if the distance is high, the linear speed will be high. And if the distance becomes 0, in this case, the linear speed is going also to become 0. So it means that we have reached the destination. So this is the linear part. The angular part is the same thing. We have to control the angle because initially, for example, the robot is looking into that direction, and it has to rotate in order to look at the direction of the goal location. Okay, so what we will do, we're going to calculate the desired angle to rotate. Okay, and for this we can use the method arctangent, and we take here as argument the y goal minus y and x goal minus x. So this is by definition is going to give the orientation between this point here and this point here. So this is the rotation that the robot has to do. And what we will do here, we will also do a proportional controller for desired angle. So we are going to multiply by a certain constant, k angular. For example, here we have set it to 4. And I'm going to show you the impact of these two constants and what happens if we change them up and down. But for now, we're just going to adjust or control the angular speed by having a proportional controller with respect to the angle to rotate. So this is the desired angle to the goal location minus the current angle. This will represent the angle to rotate. And finally, once we have set the linear speed and the angular speed, we are going to assign them to the velocity message that is defined over here. So linear.x will be equal to linear speed, and angular.z will be just equal to angular speed. And finally, we need to publish the message using a velocity message here. And if the distance is smaller than a very small value, in principle here we have to make if the distance is equal to 0. But since the distance is expressed in float, it's not possible to have exact equality to 0. So we consider here epsilon as a margin of error. We're going to put it as 0.01, which is very small. So if the distance becomes smaller than 0.01, we are going to break the loop and then make the robot stop. So this is the go-to-goal behavior. Of course, here, since we are calculating the up-to-date values of x and y, remember, like we did in the move in straight line, we need to define the pose callback function, okay, in order to make the value of x, y, and u up to date. So here we have a subscriber, okay, to the pose topic. So pose topic is /turtle1/pose, and whenever there is a new post message that is published by the ROS ecosystem, it will come here, it will execute this post callback and will update the x, y, and u coordinate. And here we are going to use the up-to-date values, both in order to calculate the current orientation of the robot and also to calculate the current position of the robot, and then deduce, or as a consequence, we can determine and calculate the distance to the goal location. And we will use the distance and the angle here, the desired angle to rotate, in order to control the speed, the linear speed, and the angular speed. So this is the code in C++. We define the method moveGoal, and this method takes two arguments. One argument that is the goal position, and here we define it as a TurtleSim pose object. And here we specify the distance tolerance. This is the epsilon that we have to make 0.01 okay, to consider that the robot has reached the destination. And we define the twist message as we did in Python. We call it here velocity message. And same thing, we define Kp is the proportional gain for the linear velocity, and Ki is the proportional gain for the angular velocity. And in the same thing, we calculate the distance. So here I have defined a method that is called getDistance. You can find it in the code. It will just, the method getDistance, it will just calculate the Euclidean distance of between two different coordinates, or between two different points. It will take the current turtle C pose and also the goal pose that we have defined in the argument of the method. Finally, if we determine the distance, the linear velocity message dot x will be equal to the proportional gain multiplied by the distance, and the angular velocity message will be just equal to the angular gain. Here it's 4, and we use the same expression to calculate the angle between the two vectors using arctangent 2 minus the current orientation of the robot. So this one is going to give the angle between the two vectors, and this is actually the angle that we need to rotate, and this is the current orientation of the robot, and then the difference will give us how much the robot has to rotate. And then we will use this angle difference to control the angular speed. And finally, we publish the message, and we use ROS once because we are in the C++, and we sleep for some time. That's the whole thing. It's very similar to the Python code. And at the end, if we reach the destination, okay, we are going to enforce the robot to stop by publishing a velocity message equal to 0. Okay, so here we are going to compile in the while loop if the distance is greater than the distance tolerance, so we keep moving. And if it becomes smaller of the distance tolerance, it will just make the robot stop because it has reached the destination. And here, of course, we define the pose callback function in C++. This is the pose message, and whenever the pose message arrives, we will use it in order to update the turtle scene pose variable. Turtle scene pose.x, turtle scene pose.y, and turtle scene pose. Okay, so this is the behavior of the go to goal. Let's now see a demonstration. Okay, so let's now illustrate the go-to-goal behavior. I'm going to activate this in the main function of the Python code. So now I'm in the main function here. And we're going to ask the robot to go to the location at x equal to 1 and y equal to 1. So this is our turtle sim. It's located here. And we will ask the turtle sim to go to this location over here. So let's go to the method go-to-goal function. Of course, here you need to find x goal, y goal. This is what we have provided, 1.0 and 1.0. And here, let me put the value of, this is the proportional gain for the distance controller, equal to 0.5. And the proportional gain for the angular controller is equal to 4.0. And then the controller is going to execute both. So it will provide both a linear velocity and angular velocity for the robot to move, which will be published. And I will put here a rate of 10 messages per second. So we have everything ready now. We can try to make the robot move to this location. So starting now the simulator, and you can see the robot is moving smoothly, and you can see now the x coordinate, the y coordinate of the robot in real time, and also the distance to go. So look, when the robot reaches, it's going to move very, very slowly because the velocity is proportional to the distance. So when the distance becomes very small, also the speed is going to become very small. That is why it will spend some time until it reaches the exact location. And it's not really at the exact location, but at a certain margin of 0.009, because here we put the value of if the distance is smaller than 0.01. Okay, we can try also to send the robot to another location. So let me put, for example, here 7 and 3. We can execute again. And the robot is going to move to that location, as you can see. Okay. So you can see that both the rotation speed and also the linear speed are proportional to the angle to rotate and also to the distance respectively. So let's see now the impact of the gains. Of course, here in the PID controller, we have to put the gains such that it provides us a smooth control of the motion. Because sometimes if you put very high values of the proportional controller, the robot will become unstable. So let me put, for example, here a value of 20 just to test. Okay, so you can see now what is the behavior of the robot. I'm going to send the robot to the same position 1, 1 that I have sent before. And you can observe now what will be the behavior of the robot. So it will start oscillating. It will start oscillating because the controller oscillates at very high speed because the gain is very high. So you can see if you don't choose the gain appropriately, in this case you can have an oscillation behavior similar to this one, and this is something that we want to avoid. Okay, so let's put this back, for example, to 1.0, and we can try it again. So let me run, and it works pretty much fine. Okay, so this is to illustrate to you that the choice of the proportional gain, whatever, for the linear velocity controller or for the angular velocity controller has to be done with care. There is no rule to say how to set it, what is the best value to set, but you can try different values until you can see that the behavior is smooth. This is how the PID controller works. Okay, so now with this we have already completed. So the move in straight line, rotate, clockwise and counterclockwise, and also the go-to-goal behavior. So let's see how we can set an absolute orientation for the robot. Another function is set desired location. Okay, and set desired location here, it's a little bit different from rotate, because rotate we provide as input a relative angle to rotate. But the set desired location, we are going to provide an absolute direction to rotate. So this is here, we're going to provide the publisher, the speed in degree, and the desired angle in degree. So it's different from the previous rotate function, because in the rotate function we provide you, for example, rotate 20 degrees. It doesn't mean go at the direction 20, no, but you have to rotate 20 degrees with respect to your current orientation. However, in the set desired orientation, we have to rotate for the absolute orientation that is desired. Okay, so what do we do here? We are going first to calculate the relative angle, which will be just the difference between the desired angle and the current angle. Of course, the desired angle, we have to convert it from degree to radians, and the U here, this is the global variable that we use to store the current orientation of the robot. And we have to specify whether to rotate clockwise or counterclockwise. How do we do this? From the sign of the relative angle radians. If the sign is negative, it means we are going to rotate in the clockwise direction, and if the angle is positive, we are going to rotate in the counterclockwise direction. And then we'll just call the method rotate by providing to it the relative angle information that we have calculated here, and it will rotate until the desired location is met. So here we are going to reuse the method rotate that we have defined before, okay, in order to implement the desired orientation, because the orientation is going to be specified by the desired angle here as an argument of the method. So same thing in C++. We define the desired angle in radians. Okay, I did it in radian, but it can be also in degree. We calculate the relative angle, then the sign, the clockwise, whether it is positive or negative. So if it is negative, it will return true, and if it is positive, it's going to return false. And finally, we will rotate using this speed for a certain angle in the clockwise or counterclockwise direction. Okay, let's now make a demonstration about the set orientation method. It's defined here, set orientation method. Okay, and here let me Deactivate go to goal and make set desired orientation. So here we are going to request the robot to rotate, let's say 90 degree with a speed 30 degrees per second. So in principle it will spend 3 seconds in order to rotate the 90 degrees. We can check this using Ross extension CPP turtle sim cleaner.py, and you can see now it is rotating to at the orientation 90 degrees. Now if you execute again, it will not move because it is already in 90 degrees. So this is the absolute orientation. Now if you change this orientation, for example, to 45 degrees, okay, it will rotate in the clockwise direction until it becomes at 45 degrees. Okay, we can try, for example, 180 degrees. 180, so in principle it should be looking into that direction. Okay, so this is different from the rotation or the rotation method, because here in this particular case we provide the absolute angle to rotate. Okay, so this is a demonstration about the set desired orientation. The last motion is the spiral motion, and here we also define the velocity publisher. So we are going to define two constants, Wk and Rk, and the linear velocity is going to be as a function of time. Rk is going to be incremented every time. So this means at every iteration we are going to increase the linear velocity, and we will keep constant the angular velocity. Okay, and the combination of these two motions is going to return for us the spiral trajectory. Same thing will be in C++. Okay, so the linear velocity is equal to Rk, and Rk is incremented every time by 1. And Wk is just the orientation speed, will be constant over time. And then we keep publishing. And now we will demonstrate the behavior of the spiral trajectory. Okay, so I will activate the spiral clean here. Velocity publisher, it will, and these are the parameters. This is Rk equal to 0 and Wk equal to 2. Of course, you remember that the Rk is going to change over time, while the angular velocity is going to be constant. Okay, this is the implementation of the spiral cleaner here. Rk equal to 0 initially, but here we are going to increment with 0.5, and Wk is going to be constant. If we execute this method, okay, so the turtle sim is going to rotate in a spiral trajectory, as you can see over here. Okay, so we can change the values of Rk and Wk, and you can see its impact on the trajectory. Let's run again the turtle sim simulator, and we can change the values. So here we can put, for example, the velocity Wk, we can put to a smaller value. So this will have an impact on the trajectory itself. Okay, so it makes a different trajectory, as you can see. Okay, we can also change the value of the increment here. We can with 0.1, so we don't increment too much. So you can see here, because we are incrementing too much the Rk value, that's why it's taking a very large spiral here. So I can reduce a little bit the increment for every second, and we can restart again the simulator and try again to run the function. Okay, here the spider is much smaller, as you can see. Okay, so you can adjust the behavior of the spider based on the values of Rk, of the increment here, and also about the Wk. Okay, so this is a demonstration about the spiral trajectory, and the last thing to present is to integrate all these different behaviors to develop the grid cleaner application. We have defined all the different behaviors. We can now make the grid cleaning, which is the whole cleaning application, by integrating all these different methods and behaviors. So the grid cleaning here, it takes a publisher as an argument, and then it will use all the different methods, including the go-to-goal location. Okay, so here we specify that the robot has to start from the location 1, 1. We define here a pose with x equal to 1, y equal to 1, and orientation theta equal to 0. And this will be the starting position of the robot. And then we will set the desired orientation to be equal to 0, which we have defined here. And then we will make the robot repeat several actions of move and rotations, okay, so that it will go as a grid trajectory. Inside the for loop, we define a complete cycle, which is moving first 1 meter, and then the robot has to rotate 90 degrees, then it has to move straight 9 meters, and then it has to rotate 90 degrees, and then it has to move 1 meter, and then it has to rotate 90 degrees again, and then it has to move also 9 meter straight, and finally rotate 90 degrees. So this is going to repeat 5 times, and we will see now in the demonstration that we'll have the agreed trajectory. So let us see this in the demonstration. Okay, we can now activate the grid clean method, and after executing, you can see that the robot first starts from the location 5, 5, and it will go to the location 1, 1 that we have specified using the go-to-goal behavior. Okay, this is the first method that will be executed, and when it reaches the destination, that is the goal location, it will set the desired location to 0, so it will rotate so that it will look into this direction. Okay. Okay, now the robot starts rotating to go to the absolute location of 0. Now it moves 1 meter, and then it will rotate 90 degrees, and then it will move 9 meters, exactly in the same way that we have defined into the cycle. Then rotate another 90 degrees, and move 1 meter, and then it rotates another 90 degrees, and so on. So this is going to repeat several times until the robot will complete the survey of the whole area. In the same way, we can also try the C++ version of the cleaner application by running the rosrun essential cpp turtlesim _clean _node. So this is going to invoke the C++ version, and here we have enabled the spiral trajectory in the C++ version, so we can actually change it by enabling the grid trajectory instead of the spiral trajectory. So let's go to the main method first, and then we are going to make a comment on the spiral clean trajectory, and we will enable the grid clean trajectory. And of course, since we are in C++, we need to recompile the code, otherwise the changes are not going to be effective. So let's go to the Catkin workspace, and then we can do Catkin make in order to generate again the executable. As you can see, it is now compiling, and we need to wait a little bit here. And finally, you can see here it generates a new executable turtlesim _clean _node. So now we can run this node again. We can run the node turtlesim _clean node, and you can see now it is executing the grid clean behavior. So first of all, the turtle goes to the location 1, 1. It will rotate to the absolute orientation of 0. So you can see how we have integrated all the different behaviors from moving straight line, rotating, set the desired location, and so on. There is a little bit of deviation here. It didn't go into the right direction. Maybe we can play a little bit with the loop rate in order to make the trajectory more accurate. Okay, so now congratulations, you have completed this section, and now you have all the ingredients in order to build a motion application for robots. So remember that we divided our problem into different sub-problems. We have implemented the move in a straight line, both in the forward and backward direction, and then in rotate clockwise and counterclockwise. We have also implemented a method to set the absolute orientation of the robot, another method to go to the goal location, and finally we have put all together in order to create the cleaning application as you have seen it in the demonstration. You can now try to play with the turtle seam and try to define several trajectories using the different methods that we have defined in this section. Okay, so far we have worked with a robot in an open space. Now imagine that you have a robot that is working in a real environment with different obstacles. If you are going to use the techniques that we have used in this section, so in this case the robot is going to hit the first obstacle is going to meet, and this is not a desired behavior. So in the next lectures we are going now to start looking into the perception aspect of a robot, how the robot is able to perceive the environment, how the robot is able to detect obstacles, and for this we will talk about both the laser scanners, which are an effective tools in order to know the different obstacles surrounding in the environment of the robot, and also we will use computer vision with RGB cameras so that the robot can understand also the what is going on inside his environment. So the next lectures will be talking about robotic perception, first using computer vision and then using laser scanner. In all the previous lectures, when we wanted to execute a node, we had to execute ROS-run for every node. So if we have 3 or 4 nodes, we need to call the ROS-run for 4 times to execute these 4 nodes, for example. Imagine that we have an application with, for example, 10 nodes or 20 nodes. It's not practical to just open 20 terminals and write ROS-run for all these different nodes. So the solution for this in ROS is to use what we call a launch file, and the launch file will help you to start multiple nodes at the same time. So let's see how it works. So in ROS you can define a launch file. Okay, the launch file starts with the tag launch, and you can define multiple nodes, like in this case. We define a first node, that is the turtle seam node, from the package turtle seam, and of the type turtle seam node. This is the name of the node inside the package, and you can give this node a particular name, okay, to be recognized in the ROS ecosystem. So same thing, the second node here is the turtle seam cleaner.py node that we have defined in the package ROS essentials CBP, and we will give it a name that is called the clean node, and you can give it any other name if you want. Okay, so this is the structure of the launch file. Let's see now in a demonstration. This is the launch file that we have defined, exactly the one that I presented on the slides, and we will see how we can make it work for opening 2 nodes at the same time. Now I'm going to close ROS-core and all the different nodes, and if we try to make ROS-run without ROS-core activated, so you can see we will have an error, but actually using ROS-launch, it's possible to start a launch file even without ROS-core. So we can use ROS-launch, ROS essential CBP clean.launch, and then it will open. It will first open the ROS-core and then create the turtle seam node, and also make the robot moving, because it already executes both the turtle seam node and also the cleaner.py script that we have already defined. So you can see now with the launch file, it's a convenient way to open multiple nodes at the same time, and this is better to run the nodes in different terminals, especially if you have a large number of nodes. You can observe here in the terminal that you don't see the output from the 2 nodes. This is normal because we didn't specify that to make the output to the screen. So you can easily make the output to the screen by just adding here output equal screen between double quote. And in this case, it will show you all the output of the turtle seam cleaner.py code. So let's try to launch again the clean.launch node, and you will see it will open the turtle seam and also the script, the cleaner script, and here we can see the output from the cleaner script because we have used the option output equal to script. Okay, so this is how we can use a launch file.